So this example looks a little bit tricky, primarily because you have non-whole number powered exponents in two of the terms here. But it turns out the power rule works exactly the same way no matter what the exponent is. So, well, let's just use the same exact strategies we have before. You're going to take your 3.14, bring it down in front, and subtract 1 from the exponent. So what does that give us? That gives us 3.14 x to the, okay, we have to subtract 1 from 3.14. Try not to use a calculator. You're just getting 2.14 in the exponent. Okay, so that handles the first term. Second term, we have this 0.5, and we have a negative 1 out in front, so we're going to multiply those two things, and then subtract 1 from the exponent. So here we got to be careful, because let's see what happens. You have negative 0.5, x to the, okay, so I have 0.5, subtract 1, so that gives us negative 0.5, or negative a half. So you have minus 0.5. If you absolutely must use a calculator for this, go ahead. We have the technology. Some people say, you're not going to have a calculator in the real world. Of course you are. We live in the 21st century. Yes, use a calculator if you are terrible at numbers like I am. So that was the second term. So the third term. What is the derivative of x? Hopefully you remember that. When we derive just x by itself, that just gives you 1. Okay? Because there's an implicit 1 out in front of this thing, and then the x derives away. Another way of thinking about that x is that it is a line of slope 1, and the derivative is a slope formula, so the slope is going to be 1. The derivative is 1. All right? So that's your final answer right there. Use the power rule in exactly the same way as we have thus far, no matter what ugliness you see in the exponent in terms of numbers. You can do this only when there are numbers in the exponents. If there's x's in the exponents, you're going to have to use another type of differentiation rule, which we'll talk about way later.